Hi. In this video, I'm going to talk about regular expressions in R. Regular expressions are essentially a little tiny programming language inside of R that is able to be used in doing mostly work using different strings. So just series of symbols and characters and letters and numbers and things like that. The reason why we use them, though, is that regular expressions have a lot of symbolic symbols that are able to stand in for different concepts. So, for example, a period in regular expression is not the actual period we've all come to know and love from punctuation. It stands for any character. So it's essentially a wild card for all sorts of different things. Asterisk, plus, question mark, these are what we call modifiers. They kind of modify the preceding character or characters to be either replicating a certain number of times, or in this case, the question mark actually modifies the modifier, making it act lazy versus greedy. So we'll talk about that in a few minutes. There are some symbols that represent different sections of a string. So like the beginning of a string is matched by the caret symbol. The end of the string is matched by the $sign. So they are used to anchor matches on one side of the string or the other. Very useful tools for just kind of specifying how close your match needs to be to your actual string. An escape is more complicated. We'll just come back to that one. And finally, there's an or. I can actually have multiple patterns that each one can match independently. And so I can do multiple comparisons in the same gsub. Generally, I recommend that if you need an or, maybe just split it into multiple gsubs. It's going to be a little bit more understandable for you just as a strategy. But we'll cover it and talk about it. There are, like I said, a number of other symbols. You can go to this web page. There's actually a lot of different functions inside of R that utilize regular expressions, but hopefully some of these examples help. So to move forward, I'm actually going to exit this full screen view and just show you that I did copy the code that we're talking through right now into the bottom of this comment section. So if you just wanted to copy and paste this into an RStudio session, you'll be able to follow along. So here I am demonstrating the use of a dot. So what I want you to do is take a second. This is going to be our pattern. This is going to be our replacement. This is what we're searching in. Look at this pattern, see where it matches over in this, and then try to see what should be replaced. So let me just give you a second to think about that. So hopefully, what you found is that an underscore followed by any character followed by an O occurs here. Here's another underscore, but there's no O, so it doesn't occur here. Here's another underscore, but it doesn't have any character followed by an O, so it doesn't occur here. In fact, it's not until you get to Nolan, can't even pronounce my own name, underscore followed by any character followed by a lowercase o, that you have another match. And so I said earlier, gsub is going to be my primary example tool for this grep and grepl family of tools, just because it allows you to visualize quite easily. So that if I run this and I replace this match with hyphens, I'm able to see where those matches were. Hello, this was replaced, the rest of this didn't match, and this did. That's dots. I do use dot from time to time, but my vast majority of the time I'm using it in strategies like this next line of code. So I'm actually going to trim this one first, and then we'll put that back in there and we'll talk about what's actually happening in the current example. But if I do this, it probably is my most frequently used gsub function of all time. And that's because I am often using text that looks like the following, like chromosome 01 underscore number, because it's a position on the chromosome. And what I do is I will do a match that looks for an underscore, and then I either replace everything upstream or I can go the other direction with it. And so here I've gone downstream. But what I'm doing right now is that I am finding this underscore. I am then finding any character, but modifying how many instances of that character there might be. In this case, any number of instances. So even if this was, say, like this, the underscore would still get replaced. However, this can go off for infinite because it is 0 to as many instances as I want. There is a similar but slightly distinct version called the plus modifier, which is 1 or more instances. In this case, and again, if I trim this off and I trim this down, now there is still a underscore, but there is not a dot to match. And so this one will not replace anything because there was less than 1. There was a 0 length match. But if there's any single character, now that whole thing does get replaced. So these strategies come into different usage, just depending on the situation. The original version that I had here gave you one of those examples. Here, where I am replacing everything to the right of here, except for until it finds another underscore. But the problem is, this is not just another underscore. This is 0 or infinite underscores. And so this matches from here to here, as well as from here to here, as well as from here to here, as well as from here to here. But it also matches from here to here. And this brings us to the new concept of greedy. By default, the asterisk and the plus are greedy. That is, they keep going if they can to still make a match. And since this is a match, this is an underscore followed by any number of characters followed by an underscore 0 or more times, it's currently 0, that is a match. And so even now, it all is end up getting erased or replaced. This next one that's not true though. So here's an underscore followed by any number of any characters, followed by an underscore 1 or more times. So it's only 1. I don't really need the plus here. I could just erase it and it would be the same. But let's say if I did have multiple pluses, I would still be able to replace it no matter how many underscores there were. But that's the idea. It's just different strategies for different situations. For the most part, I'm often using asterisk. That's just my go-to. A question mark is a modifier to these modifiers. It is a way to take that modifier and make it lazy. So for instance, I have an underscore followed by any number of characters a lazy number of times, followed by another underscore. In this case, all of that is going to be replaced. So if I do that, it's going to match here. And hopefully what you're asking is, well, before it would have matched this, underscore any number of characters to another underscore, but that's because the default behavior is greedy. Lazy means it stops as soon as that match is found. But it's a little bit trickier than that. It's not that it stops completely, it's just that that match ends and the new one can now begin. So at that point, it then continues. It does find another underscore followed by any number of characters, followed by an underscore. And again, that's a short match. It can now stop. Here's another underscore, but this time there isn't an underscore after the other letters. And so this is not a match. And so there are only 2 replacements. Here, replace, and here, replaced. So that is lazy. Very useful, a little bit trickier to use because it just requires you to kind of go through multiple levels of thinking. The caret symbol and the dollar symbol are both very useful for just making the match have to occur at the beginning or at the end. So for instance, here I've said at the beginning of the string, a character followed by an O, and then tell me grepl, so true or false, did you find that match? Well, this does not have an O as the second character. This does have an O as the second character. And so this is false, and then this is true. The dollar sign is just the opposite. It matches the end. So here I've said an O. This was used in the original example, followed by the end of the string. And so I can gsub, I can replace this O with 3 O's to make it hello world. So it's cool. You have all these powerful symbols, but sometimes you actually have text that has symbols. And maybe you even want to refer to those symbols inside your pattern. So that is where it gets a little bit challenging. I know this was so easy before. Now, that is another challenge to this, is that sometimes you do have to tell R that the next character is literally the period character. The problem is, and it's not that big of a problem, but the complication further is that you are communicating this to the gsub algorithm, in this case, to regular expressions. But R also uses backslashes as a special character. So in this case, in order to make your special character the actual special character backslash so that the period can be utilized, you have to backslash your backslash. Now, what you really need to memorize is that sometimes when I backslash things, I'm going to have to use 2 backslashes because of this multiple levels of interpretation thing. In fact, if I want to backslash a backslash for backslashing a backslash, I do have to use 4 backslashes. And I have just sat there some days and just be like, I don't know, let's try another backslash. Just keep putting them in. In this case, though, for an actual period, I backslash that period for gsub, and then I backslash that backslash for R. That's it. So this would work. This will replace period with space to the space. Hello to the world. Finally, I did say I would present it. I don't often recommend you actually use these because I just think they're more confusing for people. I think it's usually easier to do something like this where you just have multiple gsubs going on. But if you do want to have separate matches, depending upon some or in this case, like I'm doing a gsub, if I'm just doing a grep, I use ors all the time. But for gsub, I'm rarely using a pipe, so an or symbol. But in this case, this is going to match either an O at the end of the string, so like here, or an O 2 characters into the string, like here. This word, chromosome, not having either situation true, will not have any substitutions made. So it is just literally an or. In the end, though, much more typically for me, especially for gsub, I'm using all of this just iteratively. I'm going through and saying, all right, well, I'm going to make this D followed by an exclamation point. So if there's a D at the end of the string, it's probably world. I'm going to fill it in with an exclamation point. And then if there's an H at the beginning of the word, it's probably hello. So I'm going to replace it with a capital H. And then here I use pasto to just squish them together into a single object. Hello world. This is very common. I think this particular example is a little bit silly because it's not my actual biological data. What's much more common is I'm working with the type of data like you're looking at in the homework, and I'm parsing through and I'm looking for things like retrotransposon, and maybe the only thing I care about is if it's a retrotransposon. So I'll strip off everything else before and after the word retro. because I'm concerned maybe there's some other spellings like retroviral transposon or retrotransposon with a capital R and a retrotransposon with a lowercase r, or retrotransposon with a hyphen in between retro and transposon. Not because any of those are really the appropriate way to write them, but because these are data sets made by humans and they thus need cleaning. So I do use this type of language quite a bit. I hope this helps. We will continue with this in class, but if you wanted to work ahead or you just want a quick review, hopefully this helps. Thank you. Bye.